For our embedded system project, we developed the game The aMAZEing Race. This game is a maze traversal platform that the player uses a user-controlled rover to traverse through the maze. The maze's walls are made up using black tape, and in certain areas we use red, green, and blue tape. The red tape gives a minus 5-second penalty to the score, green gives a 5-second boost to the score, and blue gives a 1-second boost to the score. As you go through the maze, it's important that you don't go through two colored gates in a row of the same color, or else that is not allowed by the rules of the game. There are two systems that are involved in this, the rover pick system as well as the fixed observational system that is at the end of the maze to detect when the pick comes across the finish line. The hardware componentry that went into our project involves, for the observer pick, an IR sensor developed by Sharp. It's 4 to 30 centimeters, analog output type that we are able to hook up to the channel of an ADC on the pick in order to get meaningful data. We chose this IR sensor because it was available in the lab and we developed with it in the first milestone. For the rover pick, the sensor that we chose was an RGB color sensor, ECE4534 We chose this sensor because it was available in the lab from the beginning, and the RGB color sensor satisfies all the necessary functionality for our system and all of the rules that we implemented.
Here we have the rover block diagram. You can see that the RGB color sensor communicates with the pick over I2C. The pick controls the motors through the chip kit motor shield, and the left and right motor encoder values are read in via the timer 3 and 4. The pick also communicates through the Wi-Fi shield via UART. And here we have the observer block diagram. The pick communicates with the IR sensor via an ADC channel, and then that pick communicates to the server wirelessly through the Wi-Fi shield.
Here we have the rover task diagram. This pick takes motor encoder data and RGB sensor data and sends it to the server. It uses 4 threads to do this. The first thread is the motor thread, and that controls the motor encoders and reads in the encoder data values that are fed in through timer 3 and timer 4. And then the sensor thread takes in the RGB sensor values through an ISR and reads those and sends those out to the TX thread. The TX thread is responsible for outputting the JSON payload through the Wi-Fi module to the server. And then the RX thread is also responsible for reading in data from the server through the Wi-Fi module and parsing that and sending that out to the 3 different threads that it needs to go to. The RX thread gives the motor thread control data. The RX thread gives the TX thread acknowledgement numbers for the messages received, and the RX thread also gives the sensor thread a signal to go ahead and start. So here we have the fixed task diagram. It has 3 main threads: the RX thread, the TX thread, and the sensor thread. Its main role is to take the IR sensor data and send it out to the server. It does this through the sensor ISR, and it's read in through the sensor thread. This information is fed to the TX thread and sent out through the Wi-Fi module to the server. The RX thread receives acknowledgments from the server, and they get verified through the TX thread.
This is Jay Warner, and I am now going over my individual contribution for the embedded project. I wrote the software that got the IR sensor functionality working right in the first milestone. When implementing the IR sensor, I created a state machine that would take 4 IR sensor values and then in the 4th state average the 4 of them before sending that data on. This was to get more consistent IR data so that we were not getting unreliable functionality. For the rover pick RGB sensor, I implemented an I2C protocol. Initially, I did this using the dynamic implementation with the polling mode operationally, and that worked when it was individual. However, when we went to integrate, the module would break. So in order to solve this, we continued using a dynamic implementation in the MPLab Harmony configurator, but we switched into interrupt mode. And this implementation switch allowed for that functionality to start working as expected again. I also constructed the maze and designed the different routes. For the UART communication in milestone 2 of this class, I created both the transfer and receiving sides of that. This was handled by using disabled the interrupts on the transfer side until you wanted to transfer some data, at which point then you would enable it either inside or outside of the ISR, depending on where that was taking place. You would have a state machine for the transfer from a start sending standpoint, a still sending standpoint, and an end transmission standpoint. For receiving, we would simply receive the data until we finally came to a closing bracket representing the end of our JSON payload. I also set up 2 different graphs for the sensor data that would be displayed in the system. The IR sensor graph displays a single histogram that is within 2 thresholds. If the bar graph goes above the high threshold, then the rover should be in between the IR sensor and the wall. If it's in between the 2 thresholds, then the IR sensor should be seeing the wall. And if the IR sensor's data falls below the lower threshold, then there should be some kind of setup error and the IR sensor needs to be reconfigured. For the RGB sensing graph data, I have 4 sets of RGB data that are all the same data, and each of them represent the color that is being sensed. So you have the red color being sensed, the green color being sensed, the blue color being sensed, and then finally black being sensed. These are the 4 colors that we use in our system. And so using the 2 thresholds across those, if the left side of the bar graph is within those thresholds for all 3 of the R, G, and B values, then that corresponding color should be the color that the RGB sensor sees.
This is Anoop. I worked on the task skeletons for both PICs, including the queue communications between the threads. And then I also mainly worked on the motor functionality and the implementation for driving the motors and reading in the encoder values properly. The main thing I worked on was the proportional, integral, and derivative algorithm, PID for short. I had to create a fixed size stack to work with the integral portion of the algorithm. So the PID algorithm basically takes in past encoder datas or velocities and sets up correctional margins to make the motors drive in more of a straight fashion and regulate the speed without overshooting too much or undershooting too much. And lastly, I worked on the motor encoder graphing and set up line graphs that are constantly updating depending on what the velocities are for the 2 left and right motors. And that was the main tool I used to help me tune my PID algorithm. Also, I used a script that helped me set up the PID coefficient values in real time, which really worked well together with the motor encoder graphing because I could do all the testing in real time without having to reflash the board. I also configured each Wi-Fi for the observer PIC and the rover PIC. And on top of that, I set up the initial scripts to handle switching between the VT network and our own access point network that we use for our own servers.
My name is Adam, and I was responsible for the server and GUI components to our system. The first component of the server is a proxy server that we implemented because when we tried to construct GET and POST requests on the PICs themselves, the Flask framework would give us weird behavior. So we implemented a proxy server that would be the only thing interacting with that Flask framework. This proxy server connects to both the PICs and the GUI component via sockets. The way the proxy works is that there is a function for each component that connects to the proxy, and these functions are then run in parallel using the Python's threading library. These functions would listen for information on those sockets, and then depending on what information was being sent to them, whether it be simple JSON payloads or byte payloads, it would react accordingly. The Flask framework that we used is simply for the leaderboard functionality of the GUI. So it has its own database, a simple text file that it stores high scores in, and when the player or user wants to see the high scores, they hit a button on the GUI that brings them to the leaderboards. It does a GET request from the Flask framework and lists those high scores. Vice versa, when a player wins the game, they are then prompted to enter their name, and the proxy will take their name and do a post request to the Flask framework and list their name in the database. The GUI component was written using PyQt, an extension of the Qt framework. It has multiple different displays. So there's a display for the main menu where there is an option for playing the game and viewing the leaderboards. Beneath those buttons are 3 other buttons that show sensor data in graph form. And then in the game, there are control buttons and 2 displays to show the current game clock and a visual cue that lets the player know what the last color sensed was. There's also a pause button that will send the halt command to the rover and stop the game clock, and then there's a back button which quits the game and resets the game clock. When a victory is triggered by the observer pick, a command is sent from the observer to the proxy, and then from the proxy to the GUI that prompts the player to enter their name, and it shows them what their high score was, and that information then gets posted to the database in the Flask framework server. If a player hits one of the black wall borders that we have, they then lose the game and have to start over, and there's a unique display for that case as well.
There are 5 limitations on our system. The first limitation is the startup order of the different programs in the system. On the Raspberry Pi, it's important that you first initiate the proxy.py file, and then you have to run the GUI. At that point, you can either run the server.py module that handles the Flask background for the leaderboards, or you can connect either of the 2 PICs. At that point, it doesn't matter. Another limitation in our system is that the rover needs to be manually placed at the start line. We don't have an automated form to reset. A third limitation, the RGB sensor doesn't always pick up the black tape reading. Another limitation with our system is that the Y-flies don't always auto-connect well. They sometimes require us to unplug and replug the Y-fly module into the boards in order to connect correctly with the server. Sometimes it also requires us to reset the server if we had a connection in the first place. The final limitation in our system is that the I2C driver will sometimes not operate as expected, and this requires a hard reset to the board by unplugging the power.
We thought of 3 main improvements that we could make to our project. The first being that we could use a joystick instead of a GUI for a more sensitive player control. And then for the second improvement, we thought we could add our graphs into the GUI in like a tab interface where we could view our graphs in real time as we're playing the game. And then the third improvement that we thought of was that we could change the RGB color selection algorithm and have it so we didn't have to set the thresholds every time we changed to a different environment.